All right, howdy folks. Welcome back to Professor Carbon on this YouTube channel. In this video, what we're going to do is go over some Diels Alder reactions. And I understand that Diels Alder, especially trying to determine the stereochemistry, is something that a lot of students struggle with at the beginning when they're looking at these problems. And it's because there's a lot of possible combinations for what can happen. And so with that, what I'm going to do is just talk you through some of these examples, and I'll try to highlight some of the tips and tricks I use to be able to figure out what the problem or product of a Diels Alder reaction is. All right, so as with all the Professor Carbon videos, what I encourage you to do is actually take a minute and see if you can solve some of these problems. Again, if you'd like the PDFs of these before you attempt to solve the problems, you can actually download them on our Patreon page if you become a Patreon subscriber. And that'll include both the blank and the filled out versions of these. So please do take a minute, try to solve these two Diels Alder reactions, and then we have a couple of challenge ones that are on the page below. All right, hopefully you've had an opportunity to solve these. Let's just review what the Diels Alder reaction is quickly here on the first one. And so the Diels Alder reaction, remember, is a concerted 3+3 cycloaddition. And what that means is all the electrons move at the same time. When I'm in class, usually I joke that I call this the 6-electron line dance, but I went to the University of Iowa for grad school, so maybe I was around a little too much country hoedown. All right, so in this case, the 6-electron line dance, as I like to call it, is going to include all 6 electrons from 3 different double bonds moving simultaneously. So we've got 1 here, 2 here, and then 3 there. And so what we're going to do then is draw out this product. And we're always going to make a cyclohexene as part of our Diels Alder reaction. And then we're going to have a methyl group here and an aldehyde group coming off of here then. And in this particular case, we also have this bridging carbon, and so I'm going to draw that this way. Often you'll see this in cyclopentadiene, by the way. This particular diene is probably one of the most famous dienes for the Diels Alder reaction because it's super reactive. And it's super reactive because those double bonds are stuck, locked in this ring, and they're stuck with that methylene group bridging and kind of being a weak activating group on the diene as well. And so that makes cyclopentadiene very special. The other reason that it's special is often this is the molecule that we first discussed this exo-endo bit with. And the exo-endo bit is one of the things that I think students find the most confusing with these reactions. And it was first discovered and drawn this way. And unfortunately, I think that's kind of a confusing way to have it drawn. And in any event, here we have the exo position, and this is the endo position. And so the general rule is that you tend to get the endo product in most Diels Alder reactions. Now, I always struggled to draw these out, and so I made a little bit of a mnemonic for myself that I think holds true for most Diels Alder reactions. And so I'm just going to have a bulb there to be the cis substituent on the S-cis diene. And so this is the S-cis bond there. And then if we think about it, this group is going to be our point of reference. And so this group is cis to that S-cis bond. So the cis group is going to end up anti or trans to the electron withdrawing group. And so if I have a Diels Alder reaction here with an aldehyde, then I'm going to end up with my cyclohexene motif. I'll have my aldehyde here. And that cis group then is going to sit here, and that cis group is going to end up anti to the electron withdrawing group, or trans. And so that should be then the endo product that we get. And we can see that here because the cis group on this diene is that bridging CH2, and the bridging CH2 is up, whereas the aldehyde is down. So the methyl group here is the one that's co-up. So the aldehyde is down, the bridging methylene is up. And so again, the cis group on the diene ends up trans or anti to the group in the final product. The reason that's important is then when we go back and draw it in the 2D form, we can draw it like this. And of course, I'm only drawing one enantiomer of this Diels Alder reaction because cyclopentadiene is achiral, because methylacrolium here is achiral. We're going to end up with plus the enantiomer. And so I can draw that out. And there's a couple of different ways that you can draw the enantiomer. So I'm the most comfortable just changing all the stereocenters. Some people instead like to draw the actual mirror image, and I'm okay with that too. I just tend to get things kind of backwards when I try to reverse them. Turns out I can only draw things like chairs in one direction, so I'm more comfortable just changing all of the stereocenters. And so this is the enantiomer of this. This is also the enantiomer of this, and these two actually are the same molecule, just drawn flipped over. So it really doesn't matter how you do that. In my class, what I tell students to do is not to worry about actually drawing the enantiomer on an exam, because usually they're time crunched. I just ask them to say plus and to let me know that they know that they get a racemic mixture of the two Diels Alder products. But they do it with good diastereoselectivity, and that is we only get the endodiastereomer, not the exodiastereomer. Okay, hopefully that makes a little bit more sense for the Diels Alder reaction. In any event, this is a very classic Diels Alder reaction between cyclopentadiene and methyl acrolein. All right, here we have a fun one. And this one's kind of nice because we have some level of symmetry here. So going around both ways, we have esters and then our double bond, and then there's OMEs, and then there's another double bond. And so we're asked to figure out what the other starting material is in this one. And the good news is we know what this starting material is, and so that's got to be this bit. And so we have to figure out what the starting material here might look like. And we're always going to start with a butadiene, and so that's a gimme. And then, of course, this butadiene has to have some OMEs on it, and so we can go ahead and draw one of those OMEs. The question here, the really important thing, though, is to look at the stereochemistry at this particular spot. And remember, because the Diels Alder reaction is a concerted cycloaddition, or 6-electron line dance, as I like to refer to them, that means all the electrons are moving at the same time, and that gives it some level of stereospecificity. And because of that, the orientation of those substituents in the starting material is going to be directly transferred to the orientation in the product. And we kind of see that up above here, because this bridging methylene is kind of pointed to the same spot. It's going to end up in the kind of same spot on the product. And it turns out that's true regardless of if it's tethered together in a ring or not. So here, because the methoxy groups, one of them is wedge and the other one is dash, that means that they're going to have opposite alkene stereochemistry in the starting material. And so we specifically want to draw this product, or starting material. In my class, I would not accept, or I would accept for only fractional points, either this one or this one. Both of these have those OMEs either being co-trans or co-cis. And if they're co-trans or co-cis, they should end up in the same spots in the product. But in the product, we clearly got one going up and one going down. And so that means we have to have one sort of cis and one sort of trans in the starting material. And again, my point of reference there is this bond. And so the OME here is trans to that bridging bond. And this one here is cis to that bridging bond. All right, and so that clears that one up. Now, a fun thing about a lot of these Diels Alder products, by the way, is that they can do stuff after the Diels Alder reaction. So I'll show you another example of that later on. But this one is just a little pinch away from aromatizing. And so what would probably happen here is that these electrons would swing over and we kick out one of the two methoxys. I don't know which one, but it would probably be one of the two of them. And what this would end up with then is we'd lose some methanol, and we would likely aromatize this. And certainly if this didn't happen under the Diels Alder reaction conditions, we could come up with conditions to do it. And the reason for that is that aromatization is such a powerful driving force that this one has a lot of kind of incentive to give off methanol and to form the benzene structure I've shown here. And so that's one really powerful thing about the Diels Alder reaction, is that you can use it to generate aromatic products as long as you kind of set them up right with enough double bonds in the starting materials. Okay, moving on to the next one. This one's actually from a famous total synthesis paper. going back to 1997, and David Evans was a longtime expert of organic chemistry at Harvard. And this person here, Jeff Johnson, is now a very prominent organic chemist too. And so this reaction is really exciting, not only because it's a fun Diels Alder reaction, but also because the authors are some of the most preeminent scholars in the area and have been for quite some time. Okay, and looking at the starting material here, it's not exactly clear how we're going to get a Diels Alder reaction out of this one, but we do have a diene here, and we do have an alpha beta unsaturated carbonyl over here that should be activated. And so let's just draw this perhaps in our butadiene fashion, and then let's just number some of these groups. So if I have 1, 2, 3, 4, I would have 1, 2, 3, 4. So that's good. Then I need 5, 6, 7, 8, 9, 10 to get me to that carbonyl. So 4, 5, 6, 7, 8, 9, 10. So 10 then would have just make sure I didn't make any mistakes. 5, 6, 7, 8, 9, 10. Okay, so that should be okay. And now we can imagine this Diels Alder reaction happening this way. Oops, not that arrow. And remember, we always get a cyclohexene out of the Diels Alder reaction regardless. And the carbon 1 here is going to have this R group dangling off of it. And then this one is going to have to go up to carbon 4. And then the one over here will have to have our carbonyl 10 and R2 coming off. So that should be the general motif. And now the question is, how many carbons do we connect with? So again, if I go to a different color here, carbon 4, so I need 1, 2, 3, 4, 5 bridging ring. And so now just so I don't make any mistakes, let me add numbers into all of these. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that looks okay now. And now the question is, do we go exo or endo? And we have all kinds of like stereochemistry involved in this one. It's actually going to generate 4 new stereocenters. And by the way, the starting material looks achiral, and this one looks like it's going to have a bunch of stereocenters. So let's put plus n here just to cover our bases. And now looking at it, let's just talk this one out loud. So here's my frame of reference in my butadiene group. And it looks like this is a trans double bond. And it looks like this one is a trans double bond. And so whatever stereochemistry this group has, this group's going to have that same stereochemistry. And let's just pick wedge because it's a little bit easier to draw. I'm just gonna do that. And then this alkene is going to be trans as well. So we're going to need to make sure wherever we end up on this thing that we have the trans stereochemistry there. And so let's just note that trans here too. And so we'll want to make sure we get there. And now we're going to have to invoke our exo-endo. And by the way, the reason I didn't mark the trans over here yet is because it's unclear to me if it should be trans this way or trans this way. And we're going to have to use exo-endo to figure that out. And so remember the cis substituent. And so let me draw in one of the cis substituents here. In this case, both cis groups are H's in that system. And so the cis substituent should end up anti to the electron withdrawing group. So both my cis substituents in this case are down. So that means I want the electron withdrawing group up. Whoa, accidental zoom in. So there we go. And now because I want to make sure whatever the 9-10 group is trans to the 7-8 group, that means this one's got to be down. That means I got to have an up H there, and I'd have a down H here. And so that should talk through that really complicated Diels Alder reaction. So that one's super complicated, both because it's intramolecular, but also because you get all of this competing stereochemistry. So that's quite interesting. The next one here is a famous one as well, and this is a diene developed by the Danishevsky group in the 70s, and it's really exciting because it's set up where these two oxygen-containing groups kind of co-boost the reactivity of this diene. And unlike our ones up above where we had symmetric dienes or symmetric dienophiles, in this particular case we have an unsymmetric system here where the double bond has an electron withdrawing group up and down, and the diene here has oxygens on different spots. And it turns out you're always going to get the kind of ortho or para version. And I personally don't like that nomenclature because ortho and para are special for benzene rings, and we're not going to make a benzene ring here. And so I don't really know how it got used, but in any event, it's kind of the terminology. And so we can just take these electrons and move them over here, and those are going to go there, and then we'll do our Diels Alder reaction this way. So we'll get this kind of a piece out, and now we have to consider the stereochemistry yet again. And so yet again, remember the cis substituent on the diene, which in this case is H, should end up anti to the electron withdrawing group. So I'm just going to put the electron withdrawing group as a wedge, and then I'll put a dash over here, and that means that that cis substituent, which is H, should go down, and the OMe should come up. And because, again, this is achiral and this is achiral, we should really put plus ent over here just to cover our bases. Okay, so that would be what I would imagine. Now, this is a cis alkene, and so we're going to make sure that this is cis as well over here in our product. And so that's kind of fun. What's nice about this is you get the cis decalin motif, and that's different from what you typically get with aldol reactions or Robinson annulations, where you get an alpha-beta unsaturated system, and then it typically reduces trans. Another really fun thing about the Danishevsky diene is if you throw in a little pinch of acid, you can hydrolyze this system to kick off this OCH3 after it's protonated. And most commonly, you end up with an alpha-beta unsaturated ketone. Now, in this particular case, it's a little bit nebulous because we can enolize and move that double bond around, but it's more just illustrative that you can get this kind of illumination after the Diels Alder reaction. And so the kind of the second reason that Danishevsky's diene is so popular is because you get this very common and very powerful substructure in the form of an alpha-beta unsaturated ketone that can be utilized or taken advantage of later in synthesis. All right, so that sums up this video on the Diels Alder reaction. Again, if you're enjoying Professor Carbon, please do subscribe to the YouTube channel. We really appreciate that. Watching that number tick up really has given some encouragement to continue making these videos, and I'll keep making them as long as folks keep subscribing and taking advantage of the resource. So with that, please share with your friend and feel free to watch the next video.